Imagine a spacecraft no larger than a city block, drifting silently through the cosmic void between stars. Its sleek hull catches the faint light of distant suns as it glides effortlessly through space at velocities that would make our fastest rockets seem like they're standing still. This vessel doesn't rely on massive fuel tanks or thunderous chemical explosions. Instead, it harnesses something far more elegant and powerful: the complete annihilation of matter itself, releasing pure energy in quantities that dwarf anything we've ever achieved. This is the promise of antimatter propulsion, perhaps humanity's most ambitious dream for reaching the stars. Hi, I'm Luna, and if you love falling asleep to curious science, quiet wonder, and starlit night stories, you're in the right place. So grab your coziest blanket, get comfy, and don't forget to hit like and subscribe, because tonight, we're embarking on a gentle journey through the cosmos, exploring one of the most profound questions facing our species. How might we one day slip the bonds of our solar system and venture forth to touch other worlds orbiting distant stars? We'll drift through the elegant physics of antimatter, discover why it represents the ultimate rocket fuel, and contemplate what it might mean for humanity to become a truly interstellar civilization. The stars have called to us since our ancestors first looked up at the night sky and wondered what lay beyond the familiar patterns of light. Tonight, as you settle into comfort and let your mind wander among these cosmic possibilities, we'll explore together the science that might one day carry us to those distant points of light, transforming them from mere sparkles in the darkness into new homes among the stars. To understand why antimatter rockets represent such a revolutionary leap in our ability to travel between stars, we must first journey into the fundamental nature of matter itself. In the quiet depths of atoms, in spaces so small that they exist beyond our everyday experience, lies a story of perfect symmetry and profound energy that has captivated physicists for nearly a century. Picture, if you can, the most familiar particle in the universe, the electron. This tiny bit of matter, with its negative electric charge, spins endlessly around atomic nuclei in a dance that has continued since the first moments after the Big Bang. Now imagine its perfect mirror image, identical in every way except for one crucial difference. Its electric charge is positive rather than negative. This is the positron, antimatter's answer to the electron, a particle that exists in perfect opposition to its matter counterpart. When Paul Dirac first predicted the existence of antimatter in 1928, he was solving equations that described the behavior of electrons at speeds approaching that of light. His mathematics, elegant and precise, suggested something remarkable. For every particle in nature, there should exist a corresponding antiparticle with opposite charge. It was a prediction born from the pure beauty of mathematical symmetry, suggesting that the universe itself might be constructed on principles of perfect balance. The discovery came just 4 years later, in 1932, when physicist Carl Anderson was studying cosmic rays high in the atmosphere. In the trails left by these energetic particles as they passed through a cloud chamber, he found something unexpected: the unmistakable signature of a positively charged particle with the same mass as an electron. The positron had revealed itself, confirming Dirac's theoretical prediction and opening our eyes to an entirely new realm of physics. But antimatter's most profound property becomes apparent when it encounters ordinary matter. Unlike chemical reactions, which rearrange atoms and release modest amounts of energy, or nuclear reactions, which transform atomic nuclei and release considerably more, the meeting of matter and antimatter results in complete annihilation. Every particle is transformed entirely into energy, following Einstein's famous equation E equals mc2 with perfect efficiency. It's as if the universe has revealed its deepest secret, that mass and energy are simply different forms of the same fundamental reality. Consider the implications of this perfect conversion. When we burn chemical fuel in a rocket engine, we're accessing less than a billionth of the mass energy locked within the fuel's atoms. Even nuclear fission, the process that powers atomic reactors and weapons, converts less than 1% of mass into energy. But antimatter annihilation converts 100% of mass into pure energy, releasing more power per unit mass than any other process known to physics. This isn't merely a theoretical curiosity confined to physics textbooks and research laboratories. Antimatter exists all around us, though in quantities so small they're measured in individual particles rather than grams or kilograms. Cosmic rays constantly create antimatter particles when they collide with atoms in our atmosphere. Radioactive decay in certain isotopes produces positrons that briefly exist before finding electrons and annihilating in tiny flashes of gamma radiation. Even bananas, with their naturally occurring potassium-40, generate about 15 positrons every hour. The challenge, of course, lies not in antimatter's existence, but in its practical application. Every positron created in our atmosphere finds an electron and annihilates within microseconds. Every antiproton produced in a particle accelerator must be carefully contained using magnetic fields, isolated from all ordinary matter to prevent its immediate destruction. We can create antimatter, store it briefly, and even use it in specialized applications. But the quantities remain vanishingly small and the costs staggeringly high. Yet these challenges, formidable as they appear, may not be insurmountable. Just as the first nuclear reactors seemed impossibly complex to earlier generations, the technologies needed to produce, store, and utilize antimatter may eventually yield to human ingenuity and determination. The potential rewards, after all, are nothing less than the stars themselves. To appreciate why antimatter represents such a revolutionary advance in rocket technology, we must first understand the fundamental principles that govern all spacecraft propulsion. Every rocket, from the smallest model launched in a backyard to the massive Saturn V that carried astronauts to the moon, operates according to Newton's third law of motion. For every action, there is an equal and opposite reaction. A rocket moves forward by throwing mass backward, and the faster that mass is expelled, the more efficient the rocket becomes. This principle, simple in concept yet profound in its implications, leads us to one of the most important concepts in rocket science: specific impulse. Think of specific impulse as a measure of how much thrust you can generate from a given amount of fuel, or alternatively, how fast you can accelerate your exhaust. Chemical rockets, burning hydrogen and oxygen or similar combinations, can accelerate their exhaust to speeds of perhaps 4 kilometers per second. This sounds impressive until we consider the vast scales involved in space travel. To escape Earth's gravitational well and reach orbit requires velocities of about 8 kilometers per second. To journey to Mars demands velocity changes of 12 kilometers per second or more. To reach the nearest star, even with gravity assists from planets and centuries of travel time, would require velocity changes measured in hundreds of kilometers per second. The mathematical relationship between fuel requirements and final velocity is exponential, meaning that as your desired speed increases, your fuel needs grow not just rapidly, but catastrophically. This is where antimatter's perfect energy conversion becomes transformative. When matter and antimatter annihilate, they produce energy in the form of high-energy photons and various particles, moving at speeds approaching that of light itself. In principle, This means exhaust velocities measured not in kilometers per second, but in significant fractions of light speed, tens of thousands or even hundreds of thousands of kilometers per second. Such exhaust velocities would revolutionize space travel in ways that are difficult to fully comprehend. A spacecraft using antimatter propulsion could accelerate continuously for months or even years, gradually building up to speeds that would carry it between stars in decades rather than millennia. The exponential fuel requirements that make interstellar travel so challenging with conventional propulsion would become manageable, even modest. But the physics of antimatter propulsion presents us with challenges as elegant as they are difficult. When a proton meets an antiproton, their annihilation doesn't produce a simple, directed beam of energy. Instead, the reaction creates a shower of particles, charged and neutral pions that quickly decay into muons, neutrinos, and gamma rays, each carrying away a portion of the available energy in different directions. Managing this complex symphony of particles and energy becomes one of the greatest engineering challenges in all of physics. The charged particles can, in principle, be directed using powerful magnetic fields, channeling them into a coherent exhaust stream. The gamma rays, being electrically neutral, pass straight through any magnetic field and represent energy that cannot be directly harnessed for propulsion. The neutrinos, nearly massless and barely interacting with matter, carry away a significant fraction of the energy while contributing nothing to thrust. It's as if nature has conspired to make even perfect fuel less than perfectly efficient. Various antimatter engine designs have been proposed to address these challenges, each representing different compromises between theoretical performance and engineering practicality. Some designs envision directing the annihilation products through magnetic nozzles, using the charged particles for thrust while simply accepting the losses from gamma rays and neutrinos. Others propose more exotic approaches, using the gamma rays to heat a conventional propellant, or even attempting to create directed beams of antimatter particles for more controlled annihilation. Perhaps most intriguing are designs that propose using antimatter not as a direct propulsion method, but as an energy source for other advanced propulsion concepts. The enormous power density of antimatter annihilation could drive fusion rockets to unprecedented performance levels, or power exotic propulsion systems like beam-powered sails, or even more speculative concepts like manipulating spacetime itself. These engineering challenges, while formidable, pale in comparison to the fundamental question of antimatter production and storage. Creating meaningful quantities of antimatter requires particle accelerators of enormous size and power consumption. Current facilities can produce antimatter only in quantities measured in billionths of a gram, at costs that would bankrupt nations if scaled up to the amounts needed for interstellar missions. Yet as we consider these obstacles, it's worth remembering that many of the most revolutionary technologies in human history once seemed equally impossible. The idea of harnessing nuclear energy for practical purposes was considered fantasy just decades before the first nuclear reactors began operating. The electronic devices that surround us today would have seemed like magic to scientists from a century ago. Perhaps antimatter propulsion, too, awaits only the right breakthrough, the crucial insight that will transform it from scientific curiosity to practical reality. In the quiet depths of research laboratories around the world, teams of physicists and engineers work with some of the most exotic matter in the universe. Using machines that stretch for kilometers underground, they accelerate particles to nearly the speed of light and crash them together with energies that briefly recreate conditions from the first moments after the Big Bang. Among the shower of particles created in these collisions are antiprotons and other antimatter particles, existing for fleeting moments before they encounter ordinary matter and vanish in flashes of pure energy. Creating antimatter is, in many ways, one of the most technically demanding endeavors in all of science. The process requires enormous particle accelerators, like those at CERN in Switzerland or Fermilab in the United States, machines that represent some of the most complex and precise instruments ever built by human hands. These facilities can produce antimatter, but only in quantities so small they're measured in individual particles, or at best, billionths of a gram. To put this in perspective, consider that the entire world's annual production of antiprotons amounts to perhaps a few billionths of a gram. This tiny quantity, if it could be annihilated all at once, would release about as much energy as a small firecracker. Yet creating this minuscule amount requires the full output of some of the world's largest and most expensive scientific instruments, consuming megawatts of electrical power and costing hundreds of millions of dollars. The physics behind antimatter production is both elegant and incredibly inefficient. When high-energy protons collide with a target material, the tremendous kinetic energy of the collision can be converted into new particles, including antiprotons. But this process follows the laws of conservation, meaning that for every antiproton created, several other particles are also produced. The antiprotons emerge with a wide range of energies and directions, requiring complex systems of magnetic fields to collect, focus, and slow them down to manageable speeds. Even under ideal conditions, only a tiny fraction of the input energy ends up stored in the form of antimatter. Current estimates suggest that creating a single gram of antimatter would require energy equivalent to the entire annual electrical output of the United States. This represents an efficiency so low that it challenges our ability to even conceptualize practical antimatter production using current methods. But perhaps more challenging than production is the question of storage. Unlike ordinary fuels that can be kept in simple tanks, antimatter must be prevented from ever touching any ordinary matter. A single antiproton meeting a single proton will result in annihilation, releasing energy that, while tiny on an absolute scale, is enormous compared to the mass of the particles involved. Scale this up to meaningful quantities, and any containment failure would result in an explosion that makes nuclear weapons seem tame by comparison. Current antimatter storage relies on magnetic and electric fields to suspend charged antimatter particles in perfect vacuum, never allowing them to touch the walls of their container. The most advanced storage systems, called penning traps, can hold antimatter particles for hours or even days. But they work only with tiny quantities, measured in millions or billions of individual particles. Scaling these systems up to hold the gram quantities needed for practical applications presents engineering challenges that strain our current understanding of materials science and magnetic field generation. The energy requirements for maintaining these magnetic containment fields add another layer of complexity. Storing significant quantities of antimatter would require powerful superconducting magnets operating continuously, themselves consuming considerable energy and requiring sophisticated cooling systems to maintain the near-absolute zero temperatures needed for superconductivity. It's as if the fuel itself demands a continuous supply of energy just to exist in storage. Yet despite these seemingly overwhelming challenges, research continues on multiple fronts. Scientists are exploring new methods of antimatter production that might be more efficient than current particle accelerator techniques. Some proposals involve using intense laser fields to create matter-antimatter pairs, potentially offering better energy efficiency than traditional approaches. Others investigate the possibility of harvesting antimatter from natural sources, such as the radiation belts around planets, where cosmic ray interactions create small quantities of antiparticles. Storage research, too, continues to advance. New magnetic bottle designs promise to hold larger quantities of antimatter for longer periods. Research into neutral antimatter, such as antihydrogen atoms, might eliminate some of the challenges associated with magnetically confining charged particles. Some visionary proposals even suggest that antimatter might be stored in the form of exotic matter states or crystalline structures that would be stable for extended periods. Perhaps most intriguingly, some researchers are exploring whether the challenges of antimatter production and storage might be bypassed entirely through in situ generation, rather than producing antimatter on Earth and carrying it as fuel. Future spacecraft might generate antimatter as needed using onboard particle accelerators powered by fusion reactors or other advanced energy sources. This approach would eliminate the storage problem while potentially making antimatter propulsion more practical for long-duration missions. As we contemplate these technical challenges, it's worth considering that they may not be permanent barriers, but rather problems awaiting solutions. The history of technology is filled with examples of seemingly impossible challenges that yielded to human persistence and ingenuity. Nuclear energy, electronics, space flight itself, all were once considered impossibilities by respected scientists. Perhaps antimatter propulsion, too, awaits the key insights that will transform it from laboratory curiosity to the engine of interstellar exploration. In laboratories around the globe, teams of dedicated researchers are quietly pushing the boundaries of what's possible with antimatter technology. Their work, often conducted in the shadows of more visible scientific endeavors, represents humanity's most serious attempt to transform theoretical physics into practical interstellar propulsion. Each experiment, each incremental advance, brings us a small step closer to the stars. At CERN, the European Particle Physics Laboratory nestled beneath the Swiss-French border, the Antimatter Decelerator Complex represents one of the world's most advanced antimatter research facilities. Here, scientists working on projects with names like ALPHA, ASAC and Aegis are not just creating antimatter, but learning to manipulate it with unprecedented precision. They've succeeded in creating and storing antihydrogen atoms, complete antimatter atoms consisting of antiprotons and positrons, for periods measured in minutes rather than microseconds. This achievement, while it might seem modest, represents a profound breakthrough in our understanding of antimatter behavior. For the first time, researchers can study antimatter atoms in detail, measuring their properties and confirming that they behave exactly as theory predicts. More importantly, for propulsion applications, the techniques developed for creating and manipulating antihydrogen are laying the groundwork for larger-scale antimatter handling systems. NASA's Jet Propulsion Laboratory has been conducting theoretical and experimental research into antimatter propulsion for several decades. Their studies have explored various engine configurations, from simple antimatter-catalyzed engines that use small amounts of antimatter to trigger more conventional fusion reactions, to pure antimatter rockets that rely entirely on matter-antimatter annihilation for thrust. Their calculations suggest that even antimatter-catalyzed systems could enable round-trip missions to nearby stars within human lifetimes. One particularly promising approach being investigated is the concept of antimatter-catalyzed microfission. In this design, tiny amounts of antimatter, perhaps just micrograms, would be used to initiate fission reactions in specially designed fuel pellets. The fission products would then be directed through magnetic nozzles to provide thrust. While not as efficient as pure antimatter annihilation, this approach would require far smaller quantities of antimatter, potentially making it achievable with nearer-term technology. European researchers have been exploring the possibility of using antimatter to drive advanced fusion rockets. Their designs envision using antimatter annihilation to achieve the extreme temperatures and pressures needed to ignite fusion reactions in lightweight fuel like hydrogen or helium. The fusion reactions would then provide the bulk of the energy for propulsion, while the antimatter serves as a highly efficient ignition system. Such an approach could potentially achieve exhaust velocities of tens of thousands of kilometers per second, while requiring only small quantities of antimatter. Perhaps most intriguingly, some researchers are investigating whether antimatter production might be revolutionized through entirely new approaches. Intense laser facilities, capable of creating electric fields that approach the fundamental limits of what spacetime itself can support, might be able to tear virtual particle pairs from the quantum vacuum, creating matter and antimatter directly from pure energy. While such techniques remain highly speculative, they offer the tantalizing possibility of producing antimatter far more efficiently than current particle accelerator methods. The storage challenge, too, is seeing innovative approaches. Researchers at Penn State University have proposed using carbon nanotube structures to store positrons in stable configurations, potentially allowing antimatter to be stored in solid form, rather than as isolated particles in magnetic bottles. Other groups are investigating whether antimatter might be incorporated into crystalline structures or exotic matter phases that would be stable without continuous magnetic confinement. Some of the most visionary research is exploring whether antimatter might be harvested from natural sources rather than produced artificially. The radiation belts around Jupiter contain significant quantities of antiprotons created by cosmic ray interactions with the planet's magnetic field. While the concentrations are still extremely low by terrestrial standards, they're far higher than anything we can currently produce in laboratories. Future missions might include antimatter collection systems, gradually accumulating fuel for interstellar missions over periods of years or decades. Recent theoretical work has also suggested that antimatter propulsion might not require the massive quantities originally thought necessary. More sophisticated engine designs, using magnetic nozzles and plasma manipulation techniques derived from fusion research, might be able to achieve high exhaust velocities with far less antimatter than earlier calculations suggested. Some proposals suggest that kilogram quantities, rather than tons, might be sufficient for interstellar missions. The field is also benefiting from advances in related technologies that weren't originally developed for antimatter applications. Superconducting magnetic systems, originally designed for fusion reactors and particle accelerators, are becoming more efficient and reliable. Cryogenic systems for maintaining near absolute zero temperatures are becoming more compact and energy efficient. Plasma physics research is yielding new techniques for manipulating charged particles at high temperatures and densities. Computer simulations are playing an increasingly important role in antimatter research. Modern supercomputers can model the complex particle interactions involved in antimatter annihilation with unprecedented detail, allowing researchers to optimize engine designs before building expensive prototypes. These simulations are revealing new possibilities for directing and controlling the energy release from antimatter reactions, potentially making antimatter engines far more efficient than early designs suggested. International collaboration is accelerating progress in ways that would have been impossible for individual nations. The technical challenges involved in antimatter research are so formidable that they require the combined expertise of physicists, engineers, and theorists from around the world. Joint research programs are sharing both costs and knowledge, ensuring that advances in one laboratory quickly benefit researchers everywhere. As this research continues, we're gradually building the knowledge base that will be needed for practical antimatter propulsion systems. Each experiment teaches us something new about how antimatter behaves, how it can be controlled, and how its energy might be harnessed. While the challenges remain formidable, the steady accumulation of knowledge and technique suggests that antimatter propulsion may be moving from the realm of speculation into the domain of engineering possibility. As we drift deeper into our exploration of antimatter propulsion, it's worth pausing to consider why interstellar travel matters at all. Why should humanity spend enormous resources and decades of research effort to reach other stars? The answer, like the gentle pull of distant gravity, becomes clearer when we consider the vast timescales over which our species must think if we hope to ensure our long-term survival and growth. Our solar system, for all its grandeur and complexity, represents just one small island of matter and energy in a cosmic ocean containing hundreds of billions of stars. Within our cosmic neighborhood, a sphere perhaps 50 light-years in radius lie hundreds of other stellar systems, many likely harboring planets, and some of those planets potentially suitable for life as we know it. These nearby stars represent not just destinations for scientific exploration, but potential homes for future generations of humans. The Kepler Space Telescope and its successors have revealed that planets are common throughout the galaxy. Nearly every star appears to host at least one planet, and a significant fraction of these worlds orbit within their star's habitable zone, where liquid water could exist on planetary surfaces. Within just a few dozen light-years of Earth, astronomers have identified several potentially habitable worlds. Proxima Centauri b, orbiting our nearest stellar neighbor. TRAPPIST-T-1's family of Earth-sized worlds. Kepler-452 billion, sometimes called Earth's cousin. But the distances involved challenge our very ability to comprehend them. Proxima Centauri, our nearest stellar neighbor, lies 4.3 light-years away, more than 40 trillion kilometers. Using our fastest current spacecraft, Voyager 1, a journey to Proxima Centauri would require roughly 70,000 years. Even our most ambitious proposed propulsion systems, using nuclear pulse rockets or fusion ramjets, would require centuries or millennia to reach nearby stars. Such timescales stretch far beyond human lifespans, beyond the persistence of nations or civilizations, beyond our ability to maintain technological continuity. This is where antimatter propulsion reveals its transformative potential. A spacecraft using antimatter engines could, in principle, accelerate continuously for months or years, building up to speeds that are significant fractions of light speed itself. At 10% of light speed, a journey to Proxima Centauri would require just 43 years long by human standards, but within the span of a single human lifetime. At 20% of light speed, the journey time drops to just over 2 decades, making round-trip missions conceivable for dedicated crews. Such capabilities would fundamentally transform humanity's relationship with the cosmos. Rather than being forever confined to our single solar system, we could begin the gradual expansion that would make us a truly interstellar species. The first missions might be robotic, carrying sophisticated instruments to study nearby planetary systems in detail impossible from Earth. But eventually, human crews might follow, establishing research outposts and perhaps even permanent settlements on distant worlds. The implications extend far beyond simple exploration, as our understanding of climate change, resource depletion, and existential risks has deepened. Many scientists and philosophers have come to view interstellar expansion as an essential insurance policy for human civilization. While Earth will remain our home for the foreseeable future, having established populations on worlds orbiting other stars would ensure that no single catastrophe, whether natural or human-caused, could threaten the entire human species. The psychological and cultural impacts of interstellar travel might be even more profound than the practical ones. Knowing that we can reach other stars, that we have options beyond our single planet, could fundamentally change how we see ourselves and our place in the universe. We would truly become citizens of the galaxy rather than residents of a single, isolated world. But interstellar travel would also force us to confront questions we've never had to seriously consider. How do we maintain communication and coordination across distances measured in light years? How do we preserve human culture and knowledge during journeys lasting decades? How do we ensure that interstellar missions don't become one-way trips to oblivion, but rather the first steps in building a genuine interstellar civilization? The energy requirements for interstellar missions, even using antimatter propulsion, would be enormous by current standards. A single interstellar mission might require energy equivalent to a significant fraction of Earth's total annual energy production. This suggests that practical interstellar travel might require not just advances in propulsion technology, but fundamental changes in how we generate and manage energy on a planetary scale. Yet these challenges, formidable as they appear, might also drive beneficial changes here on Earth. The technologies developed for interstellar missions, advanced life support systems, closed-loop ecological systems, ultra-efficient energy generation and storage, could find applications in addressing environmental and resource challenges on our home planet. The international cooperation required for such ambitious projects might foster the kind of global coordination needed to address climate change and other planetary-scale challenges. The timeframes involved in developing interstellar capabilities also offer a fascinating perspective on human technological development. The research and development needed to make antimatter propulsion practical will likely span decades, requiring sustained effort across multiple generations of scientists and engineers. This kind of long-term technological commitment would represent something new in human history. A project spanning generations and requiring unprecedented coordination and persistence. As we contemplate these possibilities, drifting through the implications of interstellar travel like a spacecraft gliding through the cosmic void, we begin to see how antimatter propulsion represents more than just an advanced rocket engine. It represents a potential gateway to humanity's expansion beyond Earth, the technology that might transform us from a single-planet species into true citizens of the galaxy. Whether we'll develop these capabilities remains uncertain, but the mere possibility opens vistas of wonder that can carry us gently toward dreams of distant stars and new worlds waiting among them. In the quiet halls of engineering laboratories and design studios, teams of visionaries are sketching out what might become humanity's first true starships. These aren't the sleek vessels of science fiction, with their impossibly clean lines and mysterious power sources, but rather complex machines that must obey the harsh laws of physics while carrying human crews across the vast emptiness between stars. Every component must be designed not just to function, but to function flawlessly for decades in the most hostile environment imaginable. An antimatter-powered interstellar vessel would be unlike anything humanity has ever built. The ship's structure would need to withstand not only the stresses of acceleration and the micrometeorite impacts common in space travel, but also the intense radiation environment created by antimatter annihilation. The gamma rays produced during matter-antimatter reactions penetrate deeply into materials, requiring massive shielding systems that must themselves be accelerated to interstellar speeds. The heart of such a vessel would be its antimatter storage and reaction systems. Picture magnetic bottle containment systems more precise than anything ever constructed, maintaining perfect vacuum conditions while manipulating antimatter particles with magnetic fields of incredible strength and stability. The slightest fluctuation in these fields, the tiniest contamination in the vacuum systems, could result in catastrophic failure. Yet these systems must operate reliably not for hours or days, but for decades of continuous operation during the long journey between stars. The engine itself would be a marvel of plasma physics and materials science. The antimatter annihilation would take place in a reaction chamber designed to withstand temperatures that briefly exceed those in the cores of stars. The resulting stream of high-energy particles would be channeled through magnetic nozzles that could direct and focus the exhaust to provide efficient thrust. These nozzles would need to maintain their shape and effectiveness while exposed to particle fluxes that would quickly destroy any conventional material. But the engineering challenges extend far beyond propulsion systems. An interstellar spacecraft must be completely self-sufficient for decades, carrying everything needed to sustain human life across distances where no rescue or resupply is possible. This means advanced life support systems that can recycle air, water, and organic materials with near-perfect efficiency. Every atom of oxygen, every molecule of water, must be preserved and reused countless times during the long journey. The psychological challenges of interstellar travel have led engineers to envision spacecraft more like small cities than traditional rockets. Multi-generational ships might need to house hundreds or thousands of people, providing not just basic life support, but also recreation, education, and meaningful work during the decades-long voyage. These vessels would need artificial gravity, created through rotation, requiring massive structures strong enough to withstand the stresses of spinning at speeds that create Earth-normal gravitational forces. Power systems for interstellar missions present their own unique challenges. While antimatter provides the energy for propulsion, the spacecraft's other systems, life support, computers, communications, scientific instruments, would require continuous electrical power for decades. Traditional solar panels become useless once the ship moves beyond the outer solar system, where sunlight is too weak to provide meaningful energy. Nuclear reactors might serve for shorter missions, but their fuel would be depleted long before reaching another star system. Some designs envision using a small fraction of the antimatter fuel to power the ship's systems, channeling the annihilation energy through thermoelectric converters or other advanced power generation systems. Others propose fusion reactors that could operate for decades using hydrogen fuel. The most speculative designs suggest that advanced civilizations might use the energy from antimatter annihilation to power exotic technologies we haven't yet discovered, perhaps even systems that could manipulate spacetime itself to reduce the apparent distance between stars. Navigation presents another layer of complexity that challenges our current capabilities. An interstellar spacecraft would travel so far from Earth that traditional navigation methods would become useless. The ship would need to navigate using pulsars, rotating neutron stars that emit regular radio pulses, as cosmic lighthouses. Computer systems would need to be radiation-hardened to survive decades in space, while maintaining the precision needed to keep the spacecraft on course across distances measured in trillions of kilometers. Communication systems would face the ultimate test of long-distance networking. Even at light speed, messages between an interstellar spacecraft and Earth would take years to travel each way. The spacecraft would need to operate autonomously for long periods, making critical decisions without any possibility of consulting mission control. Advanced artificial intelligence systems would be essential, not just for navigation and operation, but for providing companionship and support to human crews during the psychological challenges of interstellar travel. The construction of such vessels would require manufacturing capabilities that dwarf anything currently existing. The mass of an interstellar spacecraft, including its antimatter fuel, radiation shielding, and life support systems, might rival that of a large asteroid. Building such structures would likely require space-based manufacturing facilities, perhaps using resources mined from asteroids or other celestial bodies. The construction process itself might take decades, requiring unprecedented international cooperation and resource allocation. Quality control and reliability take on new meaning when failure isn't just inconvenient, but potentially catastrophic for the entire crew. Every component would need redundant backups, and those backups would need backups. Manufacturing tolerances would need to be tighter than anything achieved in current aerospace applications. Testing and validation procedures would need to simulate decades of operation in conditions that can't be fully replicated on Earth. Yet as daunting as these engineering challenges appear, they may not be insurmountable. Human engineering has repeatedly achieved what once seemed impossible, from spanning great rivers with bridges to landing humans on the moon. Each challenge represents a problem waiting for a solution, a puzzle that will yield to human creativity and persistence. The very act of attempting to solve these problems drives advances in materials science, manufacturing techniques, and systems engineering that benefit applications far beyond interstellar travel. As we contemplate these engineering marvels that might one day carry humanity to the stars, we're reminded that the greatest achievements in human history have always required not just scientific knowledge, but the engineering expertise to transform theoretical possibility into practical reality. The starships of the future will be humanity's greatest engineering achievement, machines that embody our deepest aspirations and most advanced capabilities, carrying us gently through the cosmic ocean toward new worlds and possibilities we can barely imagine. As we drift deeper into contemplating antimatter propulsion and interstellar travel, we must eventually confront a question that grounds even the most soaring technological dreams in practical reality. What would it cost? The economics of interstellar travel represent challenges almost as formidable as the technical ones, requiring us to think about resource allocation, international cooperation, and long-term investment on scales that dwarf any project humanity has ever undertaken. Current estimates for antimatter production costs are staggering in their magnitude. Creating a single gram of antimatter using today's methods would cost somewhere between $25 trillion and $100 trillion, more than the entire gross domestic product of Earth's most prosperous nations. A typical interstellar mission might require kilograms or even tons of antimatter, placing the fuel costs alone beyond the economic capacity of our entire civilization. But these numbers, overwhelming as they appear, may not represent permanent limitations. The cost estimates are based on current particle accelerator technology, which was never designed for efficient antimatter production, but rather for fundamental physics research. just as the cost of computer processors has dropped by factors of millions since the first electronic computers. The cost of antimatter production might plummet as dedicated production facilities are developed and economies of scale come into play. Consider the parallel with nuclear technology. In the 1940s, producing enough enriched uranium for a single nuclear weapon required the construction of massive facilities that consumed a significant fraction of the United States' wartime electrical production. Today, commercial nuclear reactors routinely use enriched uranium that's produced at costs measured in tens of dollars per kilogram rather than millions. The transformation occurred through technological refinement, improved processes, and industrial scaling that made the impossible routine. Antimatter production might follow a similar trajectory. Dedicated antimatter factories, using optimized particle accelerators or entirely new production methods, might achieve efficiencies thousands or millions of times better than current research facilities. Advances in superconducting technology, plasma physics, and materials science could dramatically reduce the energy requirements for antimatter creation and storage. The development timeline for such capabilities would likely span decades, requiring sustained investment and research effort comparable to major scientific endeavors like the Manhattan Project or the Apollo program. But unlike those projects, which were driven by immediate national security concerns, antimatter development would need to be justified by long-term benefits that might not be realized for generations. This suggests that interstellar travel development would require new models of international cooperation and long-term planning. No single nation could afford the research and development costs, just as no single nation could justify the expense for projects that might not yield benefits within current political timeframes. The development of interstellar capabilities would likely require truly global cooperation, perhaps through international organizations specifically designed to coordinate multi-generational technological development. The economic models for such cooperation remain largely unexplored. Would participating nations contribute based on their economic capacity, similar to United Nations funding models? Would contributions be based on expected benefits, with spacefaring nations contributing more than those less likely to participate directly in interstellar missions? These questions become even more complex when we consider that the benefits of interstellar travel, scientific knowledge, potential resources, long-term species survival, are difficult to quantify in traditional economic terms. The return on investment for interstellar missions operates on timescales that challenge conventional economic thinking. While the first robotic missions to nearby stars might return scientific data within decades, any economic benefits from interstellar expansion would likely take centuries to materialize. This temporal mismatch between investment and return requires us to think about economics in entirely new ways, perhaps developing new models that account for multi-generational benefits and risks. Some economists have suggested that interstellar development might be justified not by direct economic returns, but by the insurance value of species survival. Just as individuals purchase insurance to protect against low probability but high-impact risks, humanity might invest in interstellar capabilities as insurance against existential threats to our species. From this perspective, the cost of developing antimatter propulsion might be justified by the value of ensuring human civilization's long-term survival, even if the probability of needing this insurance remains small. The spin-off benefits from interstellar research could also provide more immediate economic justification. The technologies developed for antimatter propulsion, advanced materials, energy storage systems, closed-loop life support, precision manufacturing, would likely find applications in many other fields. The Apollo program, while primarily focused on reaching the moon, generated numerous technological innovations that revolutionized everything from computers to medical devices. Antimatter research might similarly drive advances that transform energy production, manufacturing, and materials science. The energy implications of antimatter technology could be particularly transformative for Earth's economy. If antimatter production ever becomes efficient enough for space propulsion, it might also revolutionize terrestrial energy systems. Small amounts of antimatter could provide enormous amounts of clean energy, potentially solving climate change and energy scarcity simultaneously. The economic value of such energy systems could easily justify the research investments needed to develop them. International technology transfer and intellectual property questions would add another layer of complexity to antimatter development economics. Would the technologies developed through international cooperation be freely shared among participating nations? How would patent rights and commercial applications be handled when the underlying research spans multiple countries and decades? These questions echo current challenges in international scientific collaboration, but on a much larger scale. The private sector's role in interstellar development remains unclear but potentially crucial. While the initial research will likely require government funding due to the enormous costs and uncertain returns, private companies might eventually play important roles in manufacturing, operations, and even mission planning. Companies like SpaceX have already demonstrated that private organizations can achieve space exploration goals that were once exclusively governmental. Future private companies might specialize in antimatter production, spacecraft manufacturing, or interstellar mission operations. Resource requirements extend beyond financial costs to include human resources of unprecedented scale and specialization. Developing antimatter propulsion would require thousands of highly trained scientists, engineers, and technicians working across multiple disciplines for decades. This human resource investment would need to be sustained even as individual researchers retire or change careers, requiring educational and training programs that could span generations. The opportunity costs of such massive resource allocation also deserve consideration. The money, materials, and human effort devoted to interstellar development could alternatively be used for addressing immediate challenges like climate change, poverty, disease, or environmental degradation. Balancing long-term interstellar goals against immediate human needs would require careful consideration of priorities and values that go far beyond simple economic calculations. Yet, as we contemplate these economic challenges, drifting through considerations of costs and benefits, like a spacecraft navigating between celestial bodies, we might remember that the greatest achievements in human history have often required investments that seemed impossible at the time. The cathedrals of medieval Europe took centuries to build, requiring sustained investment across multiple generations for benefits that were largely spiritual rather than economic. The exploration of Earth's oceans and continents required similar long-term commitments, often based more on curiosity and ambition than on clear economic returns. Perhaps the economics of interstellar travel will ultimately depend not on traditional cost-benefit analyses, but on humanity's collective decision about what kind of species we want to become. If we choose to remain forever bound to Earth, the costs of interstellar development will always seem excessive. But if we decide to become a true spacefaring civilization, reaching out to touch other worlds and other stars, Then the economic challenges become simply problems to be solved, rather than barriers to be avoided. As we journey deeper into the contemplation of interstellar travel, our minds naturally turn from the technical and economic challenges to perhaps the most complex questions of all. How would such voyages affect the human beings who undertake them? The social and psychological dimensions of interstellar travel present challenges that are simultaneously more subtle and more fundamental than any engineering problem, touching the very core of what it means to be human in a vast and empty cosmos. Imagine, for a moment, the psychological reality of departing Earth knowing that you will never return. The crew of an interstellar mission would watch their home planet dwindle to a pale blue dot, then to a point of light indistinguishable from other stars, and finally disappear entirely into the cosmic background. Unlike every previous human journey, no matter how dangerous or distant, there would be no possibility of return, no hope of rescue if something went wrong, no communication with home except for messages that take years to traverse the growing distance. The isolation would be unlike anything in human experience. Even the most remote Antarctic research stations maintain radio contact with the outside world. The International Space Station, despite being in the harsh environment of space, orbits just a few hundred kilometers above Earth's surface. But an interstellar spacecraft would be truly alone, separated from the rest of humanity by distances so vast that they challenge our ability to comprehend them. The crew would need to create their own society, their own culture, sustained entirely by what they carry with them and what they can create together. Multi-generational missions present even more complex psychological challenges. Children born during the journey would face a unique existential situation. They would be citizens of no world, belonging neither to Earth, which they've never seen, nor to their destination, which may remain decades away. How would such individuals develop their sense of identity and purpose? How would they relate to the mission's goals when they had no choice in undertaking the journey? The social structure of an interstellar mission would need to address questions that human societies have never faced. Traditional governance models assume some connection to a broader civilization, some higher authority to which appeals can be made. But an interstellar crew would be entirely self-governing, with no external legal or social framework to fall back on. They would need to develop new forms of democracy, justice, and social organization that could function in the unique environment of a spacecraft traveling between stars. Conflict resolution becomes particularly critical in environments where the participants cannot be separated. On Earth, individuals and groups in conflict can move apart, seek mediation from external authorities, or simply avoid each other. But the crew of an interstellar mission would be confined together for decades, with no possibility of escape from personal or political tensions. The social technologies for managing such conflicts would need to be far more sophisticated than anything currently available. The psychological challenges of maintaining hope and purpose across such vast timescales could prove more formidable than any technical obstacle. Human motivation typically operates on timescales of days, months, or at most years. Maintaining enthusiasm and dedication for decades-long journeys would require new approaches to meaning-making and psychological support. The crew would need to find fulfillment not just in the eventual destination, but in the journey itself, creating purpose and meaning from the day-to-day experience of traveling between stars. Cultural preservation and evolution present fascinating paradoxes. How much of Earth's culture should an interstellar mission attempt to preserve? Too much, and the crew might remain forever tied to a world they can never revisit. Too little, and they might lose essential aspects of what makes them human. The crew would inevitably develop their own culture, adapted to their unique circumstances. But how much should this culture diverge from its terrestrial origins? Communication with Earth raises its own psychological challenges. As the distance grows, messages would take increasingly long to travel between the spacecraft and home. Simple conversations would become impossible, replaced by something more like exchanging letters across an ever-growing void. Eventually, the delay would become so great that meaningful dialogue with Earth would cease entirely. The crew would need to develop psychological strategies for maintaining connection with humanity while accepting their growing isolation. The educational challenges for multi-generational missions would be unprecedented. Children born during the journey would need education not just in practical skills needed to operate the spacecraft, but in the broader knowledge and culture of human civilization. How do you teach someone about Earth's oceans when they've never seen liquid water in quantities larger than a drinking glass? How do you convey the experience of weather, seasons, or wide-open spaces to someone who has lived their entire life within the confines of a spacecraft? Religious and philosophical questions would take on new dimensions during interstellar travel. Many human spiritual traditions are closely tied to Earth, to specific places, natural phenomena, or cultural contexts that wouldn't exist aboard a spacecraft. New forms of spirituality might emerge, adapted to the unique experience of traveling between stars. The crew might develop new rituals, new ways of understanding their place in the universe, new approaches to questions of meaning and purpose. The psychological preparation for interstellar missions would likely require years or even decades of training. Crew members would need not just technical skills, but extraordinary psychological resilience, social capabilities, and personal maturity. The selection process would need to identify individuals who could not only survive the journey, but thrive during it, creating meaning and purpose from the experience itself rather than just from the destination. Mental health support systems would need to be far more sophisticated than anything currently available. Traditional therapy models assume access to a broader social environment, the possibility of changing circumstances, and connection to external support systems. Interstellar crew members would need new forms of psychological support adapted to their unique circumstances, perhaps including advanced virtual reality systems that could provide simulated experiences of natural environments, or new forms of group therapy designed for small, isolated communities. Yet despite these challenges, or perhaps because of them, interstellar travel might also represent the ultimate expression of human adaptability and resilience. Throughout our species' history, we have repeatedly adapted to new environments and circumstances, from the African savanna to Arctic ice sheets, from small tribal groups to complex urban societies. Interstellar travel would simply represent the next step in this long process of adaptation, pushing human social and psychological capabilities to new levels of sophistication. The crew of humanity's first interstellar mission would be pioneers not just in space travel, but in new forms of human social organization and psychology. Their experiences would teach us new things about human nature, about how we relate to each other, and to our environment when stripped of all familiar contexts. In learning to live between the stars, they might discover aspects of humanity that we never knew existed, creating new models for human society that could benefit even those who remain on Earth. As we contemplate these psychological and social dimensions, drifting through considerations of human nature and social organization, like travelers through the quiet spaces between worlds, we begin to understand that interstellar travel represents more than just a technological achievement. It represents a fundamental transformation in what it means to be human, a step toward becoming a species that is truly at home in the cosmos, rather than just visitors from a single, small world. In the gentle quiet of late evening, when the day's concerns have settled into peaceful stillness, our minds often turn toward the future, wondering what tomorrow might bring. Tonight, as we drift through contemplations of antimatter propulsion and interstellar travel, let us allow our imagination to wander forward through time, envisioning the world that might emerge if humanity truly mastered the art of traveling between stars. Picture, if you will, Earth in the year 2150. The planet glows softly in the darkness of space, its cities powered by fusion reactors, and its atmosphere carefully maintained through advanced environmental management systems. But Earth is no longer humanity's only home. Scattered across the galaxy, within 100 light-years of our solar system, small human settlements dot the surfaces of distant worlds, each adapted to the unique conditions of their alien environments. The journey to this interstellar future would have unfolded gradually, like the slow turning of seasons. The first breakthrough might have come in the late 21st century, when researchers finally developed efficient methods for producing and storing meaningful quantities of antimatter. Perhaps it was a new type of particle accelerator, using advanced superconducting magnets and plasma confinement techniques that could create antiprotons 1,000 times more efficiently than early 21st century methods. Or maybe it was the discovery of a way to harvest antimatter from natural sources, using automated collectors positioned in the radiation belts of gas giant planets. The first interstellar missions would have been robotic, small craft carrying sophisticated instruments to nearby star systems. These early scouts, launched in the 2080s or 2090s, might have taken 20 or 30 years to reach their destinations. But they would have returned data that transformed our understanding of planetary formation, astrobiology, and the potential for life throughout the galaxy. The discovery of living ecosystems on worlds orbiting nearby stars would have electrified human civilization, providing both the justification and the inspiration for crewed missions to follow. The first human interstellar voyages would have been journeys of extraordinary courage and commitment. Perhaps a crew of 50 volunteers, selected from thousands of applicants, would have departed Earth aboard humanity's first true starship in the early 22nd century. Their destination might have been Proxima Centauri b, the closest potentially habitable world to Earth, a journey that would take 15 years, using advanced antimatter propulsion systems. The psychological and social technologies developed for these early missions would have evolved far beyond our current understanding. The crew would have been supported by advanced artificial intelligence systems designed not just to assist with technical operations, but to provide companionship and psychological support during the long journey. Virtual reality environments would have allowed them to experience simulated Earth environments, walking through forests, swimming in oceans, feeling the warmth of natural sunlight, maintaining connections to their evolutionary heritage, even while traveling through the emptiness between stars. Communication technologies would have evolved to maintain some form of connection with Earth, despite the vast distances involved. Perhaps quantum entanglement communication systems, still theoretical today, would have allowed instantaneous transmission of at least limited information across interstellar distances. Or maybe advanced AI systems would have been developed to carry on meaningful conversations with Earth-based personalities, creating the illusion of communication, even when messages took years to travel between worlds. The transformation of human society required to support interstellar expansion would have been as profound as the technical achievements. International cooperation would have evolved beyond current models, perhaps through the formation of a true global government, or at least international institutions capable of coordinating multi-generational projects. Educational systems would have adapted to prepare people for roles in an interstellar civilization, teaching not just technical skills, but the psychological and social capabilities needed for life in small, isolated communities traveling through space. Resource utilization would have been revolutionized by the technologies developed for interstellar travel. Closed-loop life support systems, originally designed for spacecraft, might have found applications in creating sustainable cities on Earth. Advanced manufacturing techniques, developed to produce complex systems from limited raw materials during interstellar journeys, could have transformed terrestrial industry. The energy technologies needed for antimatter production and storage might have solved Earth's climate and energy challenges, providing clean, abundant power for the entire planet. The early interstellar settlements would have been small, perhaps just a few hundred people struggling to establish sustainable communities on alien worlds. But they would have represented something unprecedented in human history, truly independent branches of human civilization, developing their own cultures and societies adapted to their unique environments. Children born on these distant worlds would be the first humans who were citizens of other star systems, belonging to humanity, but not to Earth. Over time, as antimatter propulsion technology matured and became more affordable, the trickle of interstellar migration would have grown into a steady stream. Trade routes might have developed between Earth and the nearest settlements, carrying not goods too expensive to transport across interstellar distances, but information, culture, and genetic diversity to prevent the isolation of small populations. Each new settlement would have served as a stepping stone for further expansion, gradually extending humanity's reach deeper into the galaxy. The scientific benefits of interstellar expansion would have been incalculable. Direct study of alien ecosystems would have revolutionized biology, revealing new forms of life and new approaches to evolution that couldn't be imagined from Earth-based studies alone. Geology and planetary science would have been transformed by access to worlds formed under different conditions, with different histories and compositions. Astronomy and physics would have benefited from observations made from multiple star systems, providing baseline measurements across interstellar distances. Perhaps most profoundly, interstellar expansion would have changed how humanity sees itself and its place in the universe. No longer would we be residents of a single, isolated world, vulnerable to any catastrophe that might befall our planet. Instead, we would be citizens of the galaxy, a species that had learned to make itself at home among the stars. This transformation in perspective might have influenced everything from art and literature to philosophy and religion, as human culture adapted to our new cosmic context. The challenges would have been enormous, of course. Not every interstellar mission would have succeeded. Some spacecraft might have suffered technical failures during their long journeys, becoming monuments to human ambition lost in the darkness between stars. Some settlements might have failed, their populations unable to adapt to alien environments or maintain the complex technologies needed for survival. But these failures would have been learning experiences, each contributing to the gradual development of more reliable and sustainable approaches to interstellar expansion. As we envision this possible future, drifting through imagined tomorrows like a spacecraft gliding silently through the cosmic dark, we see how antimatter propulsion could serve as the key that unlocks humanity's expansion into the galaxy. Not just a technical achievement, but a catalyst for social, psychological, and cultural transformations that would make us truly worthy of calling ourselves a spacefaring civilization. The timeline for such developments remains uncertain, of course. The technical challenges are formidable, the economic requirements enormous, the social adaptations unprecedented. But human history suggests that what seems impossible today often becomes routine tomorrow. Given sufficient time, effort, and determination, the technologies and social systems needed for interstellar expansion may be decades or centuries in the future. But they lie within the realm of possibility, waiting for the right combination of scientific breakthrough, social commitment, and perhaps simple human restlessness to bring them into being. The gentle path to forever, as our journey through the cosmos of antimatter propulsion and interstellar travel begins to approach its quiet conclusion. Let us allow our thoughts to settle into the profound stillness that surrounds these vast topics. Like a spacecraft, finally reaching the peaceful equilibrium of its cruise phase after the intensity of acceleration. The questions we've explored together: how to harness the ultimate energy source, how to cross the seemingly impossible distances between stars, how to transform humanity into a truly cosmic species. These represent some of the deepest challenges and grandest dreams that our kind has ever contemplated. In the soft darkness of contemplation, we can see how antimatter propulsion represents more than just an advanced rocket engine. It embodies humanity's perpetual reaching beyond the boundaries of the possible, our refusal to accept the limitations that seem to confine us. From the first humans who looked up at the stars and wondered what lay beyond, to the physicists who first imagined particles of perfect opposition, to the engineers who today sketch designs for starships that exist only in possibility, we see the continuation of a story that defines us as a species. The technical challenges we've explored: producing and storing antimatter, designing engines that can harness annihilation energy, building spacecraft that can sustain human life across decades of travel. These represent problems of extraordinary complexity, yet they are not fundamentally different from challenges that humans have faced and overcome before. The mathematics of antimatter annihilation follow the same physical laws that govern the fusion reactions in stars and the chemical processes in our own bodies. The engineering requirements, while demanding, build upon principles that we already understand. The human factors, complex as they are, represent extensions of social and psychological capabilities that our species has been developing throughout its history. What makes antimatter propulsion particularly fascinating is how it connects the smallest scales of reality, the quantum interactions between particles and antiparticles, to the largest scales of human ambition, the desire to reach other stars and spread life throughout the galaxy. In the annihilation of a single proton and antiproton, we see the same physical principles that could one day carry entire communities to worlds orbiting distant suns. It's a reminder of how the universe operates on principles of elegant unity, where the same laws that govern the behavior of atoms also determine the motion of galaxies. The economic and social challenges of interstellar development remind us that technical capability alone is never sufficient for great achievements. The pyramids of Egypt required not just engineering knowledge, but social organization capable of coordinating massive projects across decades. The exploration of Earth's oceans demanded not just improved shipbuilding, but economic systems that could finance risky ventures with uncertain returns. Similarly, the development of antimatter propulsion will require new forms of international cooperation, new models of long-term investment, and new ways of thinking about humanity's collective future. Perhaps most intriguingly, the development of interstellar capabilities would inevitably change us as a species. The technologies required closed-loop life support, advanced artificial intelligence, precision manufacturing, energy systems of unprecedented efficiency, would find applications far beyond space travel. The social systems needed to coordinate multi-generational projects would provide new models for addressing other long-term challenges, like climate change and resource management. The psychological insights gained from studying how humans adapt to the extreme isolation of interstellar travel might help us better understand consciousness, identity, and social bonds in more ordinary circumstances. The timeline for these developments remains fundamentally uncertain. Breakthrough discoveries could accelerate progress dramatically, just as unexpected obstacles could delay it for generations. But the direction seems clear. Humanity continues to develop increasingly sophisticated technologies for manipulating matter and energy, for traveling through space, for sustaining life in hostile environments. Whether the specific path involves antimatter propulsion or some other approach we haven't yet imagined, the long arc of technological development points toward eventual interstellar capabilities. As we contemplate these possibilities in the quiet of late evening, we might reflect on how the pursuit of interstellar travel represents something uniquely human. No other species on Earth, as far as we know, contemplates journeys beyond their home environment purely for the sake of exploration and expansion. No other creatures develop technologies not just to survive, but to extend their reach into previously impossible realms. The dream of traveling to other stars reflects something essential about human nature. Our perpetual dissatisfaction with current limitations, our drive to explore and understand, our hope that somewhere among the stars we might find new meanings and possibilities. Yet there's also something deeply peaceful about contemplating these vast undertakings. Antimatter propulsion and interstellar travel operate on timescales that dwarf human concerns about daily life, political conflicts, or economic fluctuations. They remind us of our place in a universe that extends far beyond our immediate experience, suggesting perspectives that can put our current challenges into cosmic context. The stars that beckon us have been shining for millions or billions of years. They will continue shining long after our current concerns have been forgotten. This isn't a diminishment of human importance, but rather an invitation to think about significance on the appropriate scales. The gentle mathematics of antimatter annihilation, the elegant physics of electromagnetic confinement, the quiet engineering of systems designed to operate flawlessly for decades in the cosmic dark. These technical details carry an almost meditative quality when considered in the proper spirit. They represent human intelligence, applied to understanding the deepest principles of reality. Human creativity, applied to solving problems of extraordinary scope and subtlety. In working toward mastery of antimatter propulsion, we're not just developing a new technology, but continuing the ancient human project of understanding and working with the fundamental forces of nature. As sleep begins to approach, like a spacecraft finally achieving orbital velocity after a long acceleration, we can let these thoughts about antimatter and starlight settle into the quiet spaces of consciousness, where the most profound questions reside. Whether humanity will actually develop practical antimatter propulsion remains to be seen. Whether we'll use such technologies to journey to other stars within our lifetimes, or within centuries, remains uncertain. But the mere fact that such possibilities lie within the realm of physical law, that the universe permits beings like us to contemplate traveling between stars, that the same physics that created the stars also allows us to dream of reaching them. This itself is a kind of miracle that can carry us gently towards sleep and dreams of distant light. The stars continue their ancient dance in the darkness above, each one a potential destination, each one representing possibilities we've only begun to imagine. Somewhere among those points of light may lie worlds where future generations of humans will walk beneath alien skies, their presence made possible by the mastery of antimatter propulsion that researchers work toward even now. And in the quiet spaces between wake and sleep, between current reality and future possibility, we can rest in the profound comfort of knowing that the universe is vast, beautiful, and full of wonders waiting to be discovered by those brave enough to dream of reaching toward them. Sweet dreams of starlight and infinite possibility.